So, yeah, before continuing the lesson today, I think you asked me a problem in physics. That would be a good idea to solve that one first for you. And somehow because you have to repeat the test tomorrow. That's good. Yes. So you told me that there are two pendulums. Yes. So you have this pendulum here. So first of all, let me talk about one pendulum. Okay, so if you have this, we are thinking about ideal pendulums, yes? So for example, I actually deviated from this equilibrium position and assume that this angle is maximally theta max, yes? So I bring the pendulum up to this point, and then I release it. Yes. And it will start actually going back and forth. And I don't know, I saw your physics book, there are some equations there. I don't know have you studied them or not, but then it becomes like a harmonic oscillator. It goes back and forth. And then it means that if you want to measure the angle at a later time, this becomes this theta m multiplied by sine of omega t plus a phase, initial phase phi.
Oh, we haven't
you haven't
talked about the phase thing.
Okay, let me take that. Yes. So this tells you that if you deviated from the equilibrium position up to a maximum angle theta m and then release it, it will go back and forth. And if you want to know what the angle is at instant t, you put it in this formula and you calculate it. And omega is the angular frequency. Yes. So this means that, and you know that omega is related to the period using this formula.
Yes.
Now you have two pendulums. One of them is longer than the other one. So for example, you have this. And then this is another pendulum that you have here. One of them is of course going faster.
Yeah.
And what is that? The reason is that there is a relation between this, which is 2 pi square root of L over G. L is the length. So you see that 2 pi and G are constant, but the period depends on the length. So if the length is longer, the period is longer. If the period is longer, the pendulum is slower because it takes a longer time. Yes. So anyway, if you want to solve this problem, you told me that a pendulum, so I don't know which one, let me call T fast and T slow, for the faster pendulum and for the slower pendulum. So the faster pendulum actually goes faster, so it means that this period is smaller. Yes?
Yes.
The faster pendulum has a smaller period.
Yes.
So it should have a smaller length.
Yes.
Yes. Okay, then if I can write this equation once for this pendulum and once for this pendulum. Yes? So what can I do? I can write theta. I assume that this angle, this maximum angle for the pendulums are the same, so I do not change that.
But I thought the formula was supposed to have the amplitude. The amplitude times sine.
Yeah, instead of amplitude, I put theta. That's amplitude. If you want, let me clean that. Because this amplitude is not a number, it's an angle. I can just write. Yes, and then this is sine omega. Let me write theta for the fast pendulum. It becomes omega fast times t. And for the slower pendulum, you can write the same thing. A times sine, I don't know, omega slow times t. Yes. And then of course, they start together.
Yes.
But then for the first time, as I understood what you said, for the first time, they will become in phase again after 123 full cycle of the faster one.
Yes.
So it means that at time t equals to 123 times t of the faster one, this is the first time after, of course, this time, they reach to the same point.
Yes.
So this is crucial to remember. Okay, and then you told me that they have mentioned that the second one takes 122 full cycles.
Yeah, exactly.
It is not correct. The ratios are 122 over 123, and I will tell you. So you cannot say that because this take 123 full cycle, this will take 122 cycles. But you can say that the ratios of TF to TS is 122 over 123. This we can prove, and that is enough for the problem. So why is that? Because assume that you want to see if this pendulum reaches to this one, it means that they simultaneously reach to the same highest point.
Yes.
Yes? So it means that when this happens, this angle for both of them is the same.
Yes.
So I want to put them equal to see at which times these two will be in phase. Yes? So because you see, this gives me this angle, this gives me the angle for this one, this gives me the angle for this one, and I want to calculate the time at which these two angles are again the same for both of them.
Yes.
Yes? Is that understandable?
Yes.
So this is why I equate these two angles and I get this equation. Yes?
Yes.
And this is trigonometry, yes? We cancel this A, and then do you remember I told you in Math 4, this one and this one. Two signs are equal, so it means that omega F times T should be omega S times T, but plus 2n pi. Yes? And then n is an integer, yes? But here n cannot be negative. Why? Because omega f is 2 pi divided by tf times t. And this is what? 2 pi over ts, t plus 2n pi. By the way, let me simplify everything by 2 pi. So this becomes t over tf is equal to t over ts is equal plus
pi. N pi. N. Just n.
n.
Just n.
Yes? And then let me move this to the other side. And then factor a t out. It becomes 1 over tf minus 1 over ts times t is equal to n. Agree? Yes?
Yes.
And n is an integer. But in this case, from physics point of view, n should be positive.
Yes.
Yes? Because tf is smaller than ts. So 1 over tf is larger than 1 over ts. So that's a positive number. And time is also positive. So n cannot be negative. Yes? So n starts from 1, 2, 3, etc. What is the meaning of that? It means that these two pendulums start from the same point at infinitely many times. Yes? Not only at this time, but for the first time, it happens that this is for the first time. If I put n equals to 1 and calculate t from here, this is happening for the first time. If I put 2 here and calculate t from here, this is happening for the second time, and etc., etc. Yes? But I know that for the first time, the time is 123 tf. So it means that if n is 1, t is equal to 123 tf. Agree?
Yes.
Okay, then put this into this equation. So this becomes 1 over tf minus 1 over ts. And instead of this t, I put 123 tf. And instead of n, I put 1.
Yes.
And then let me multiply this here. If I multiply this tf and tf are cancelled. I get 123 tf. Sorry, tf is cancelled. This one multiplied by this one, and that one are cancelled. 123 is left. Minus what? 123 tf over ts is equal to 1.
Yes.
Now I move this negative 1 to the right, it becomes positive. Move this one to the left, and that is 122. So this becomes 122 is equal to 123 tf over ts. So this means that if I divide by that, you see I was not able to find tf and ts individually, but I was able to show that whatever this problem is, the ratio is 123 over 123. 22 over 120, and that is exactly what you need for solving that problem. Is that right?
Yes, yes, yes.
So without this calculation, it was not. I was thinking for nearly 15 minutes, but I really didn't understand how could I solve this problem. I was thinking that might be without doing some trigonometry, I will be able to do
because
that.
they just named it. They said, oh, if this is this, then
Where?
it has to
Where
be.
they did just
Yeah, in the faucet they said if it's
okay.
123, it means it's 122, and then they just went
But
on
still,
with
I
that.
don't believe that that is true. Do you understand what I mean? What we got is the ratio is 122 over 123. I don't know. I have been thinking a lot about this, but there is no guarantee that when this becomes, I don't know. What I was able to show, and I can rely on it, is the ratio is 122 over 123. Because if I change n to 2,
Yes.
you can still solve the problem and find other times, yes? But that, because that is happening for the first time, it means that you need to replace n with 1 and t with that number. So, but in this way, you can solve different methods, yes? So, yeah, I hope that this is a little bit understandable. Thank you. So let us now continue to the lesson. Today I want to talk about geometric progression. Okay, but this is also simple, so I want to finish hopefully this session. It is not hard at all. It's very similar to what we have learned for arithmetic progression. The only difference is that, let me write here, the geometric progression. So I think you have studied this in math once. Do you remember what a geometric progression is? You have a sequence of numbers, but how they are related term by term? Any ideas? Do you remember? Yes? What? No, that is common difference is, did you say common difference? Common difference is the word we use for arithmetic progression. And that was denoted by D. So for geometric progression, each term is obtained from the previous term by multiplying it by a constant number. In arithmetic progression, we add a constant number to the previous one to get the next one. But in geometric progression, we take the previous one multiplied by a constant, fixed constant number, and I get the terms after that, yes? That's probably, I don't know, you can start from 1. Each time you can multiply it by 2, for example. It becomes 2, the next time it becomes 4, the next time it becomes 8, the next time it becomes 16, 32, and etc., etc. So that's a geometric progression. And the number that I am multiplying each time is called not the common difference for a good reason. It is called the common ratio. Yes, the reason is that the ratio of 2 over 1 is the same thing as 4 over 2, is the same thing as 8 over 4, is the same thing as 16 over 8, and etc. This is called the common ratio. Yes? Okay, and in English books they show it with R. It's a little bit common ratio, yes. That was also common difference. Do you remember common difference with Joe's T? So that is the symbol we use for this number. But I think in Swedish books they show it with K. I don't know, for some reason. Okay, so I would say that my first term is T1. My second term is T1 multiplied by R. And for the third term, I would say that this is the second term multiplied by R. But the second term itself is T1 multiplied by R, so it becomes T1 multiplied by R squared, yes? And then you can continue. For example, T4 is the previous term multiplied by one more common ratio. But T3 itself is this. If I multiply it by one extra R, it becomes T1 R to the power of 3. And if you continue this list, I think it is easy to guess what will happen when I reach to the nth term. What is that? T1 is common to all of them, but multiplied by R to some power. What that power is?
N minus 1.
N minus 1. Because when it was 1, I didn't have any R's.
Yes.
When it is 2, I have 1 R. When it is 3, I have 2 R's. When it is 4, I have 3 R's. So if it is n, I have 1 less R. So that is Tn. So let me compare this one. If you want to write arithmetic progression against geometric progression, the formula that I discovered today now is this formula. If you want to write the corresponding formula from arithmetic progression, do you remember what was that? It was Tn equals to T1 plus n minus 1 d. Yes? So whatever this formula can do for you in an arithmetic progression, this formula can do the same job for you in geometric progression. They have the same roles. Yes? And by the way, of course, do you remember I told you that d can in principle be any number, any real number, but we took out one number as an exception. It doesn't mean it is not possible, but it is very boring. What that number d is? 0. Because if d is 0, every term will be 0. Yeah? It will be the same term.
Yeah.
Yes? So that is boring. So here, usually we assume that d is not equal to 0. What about this one? What it will become? Which choice of r makes it a little bit boring, my sequence? 1. Because if I choose r equal to 1, then I will generate the same sequence over and over again. And of course, here we can say more. Even 0 is not good here. Because the first term, whatever it is, the second term becomes 0, and the terms after that all become 0. So that's also not that interesting. And minus 1 is also not that interesting because it will change the sign alternatingly. Yes. Like for example, if I start with 2 multiplied by minus 1, it becomes minus 2. Multiplied by another minus 1, it becomes 2. So it alternates between 2 and minus 2. So usually, it's not mandatory, of course. The interesting cases are the cases in which r is not 0, not plus, and minus 1. But this is not a have to. Yes? It's here, d is not usually 0. Okay. Usually. Yeah, because these examples are so simple, I will not give you more. For example, let me give you one more at least. So if I have 3, and then I have 3 square root of 2, then I have 12, then I have 12 square root of 2, then I have 24, etc., etc. Do you think that's a geometric progression here, what I have written?
Yes.
Every time I am multiplying by what? Yes? A square root of 2. So here the common ratio is the square root of 2. If I multiply this by square root of 2, it becomes 3 square root of 2. If I multiply it by an extra square root of 2, square root of 2 times this is 2. Oops, I made a mistake. So, yes, yeah, it should be 6. And the next one should be 6 square root of 2. And the next one? So it was not a geometric progression. Why did you say yes? Yes. So you shouldn't actually trust me that much. Okay. So that is now a geometric progression for the square root of 2 as the common ratio. So do you remember what was the second formula in arithmetic progression? There are two main formulas. One for the nth and the sum. And we want to find a formula for the sum here as well. So the question is that let T1, T2 up to Tn be the terms, consecutive terms, from the first term to the nth term of a geometric progression with common ratio r. And Sn is exactly as before. Sn means the sum of the terms from the first term to the nth term. I want to find a closed formula for Sn. By closed formula, it means that something equal to this without containing these 3 dots. And of course, the numbers that I give you is r and T1. I want you to write a formula for Sn so that if you know T1 and if you know r, you can put these numbers into that formula and find Sn. Okay, do you remember what was the idea behind proving the formula for the arithmetic progression? I don't want the details, but what was the idea? So do you remember we had this formula? So we wrote it in two different ways. N times T1 plus Tn divided by 2. And we also write it as N times 2T1 plus N minus 1D divided by 2. Okay, we want to find the formulas here for geometric progression. What was the idea? If you remember, I proved this formula for you. But how did I do it? Don't you remember? Do you remember how I calculated the sum from numbers 1 to 199 or something? How did I do that?
Did you pay?
How? I rewrote it first in the reverse order and add them.
How many D's are there in that?
Yeah, exactly. So the idea was to write this the other way around and add them term by term. Yes? And then of course I will get 2 times that number, then at the end I divide by 2. This is why this division by 2. So what is your suggestion for this one now? I want to find, so the question is that I want to add these numbers, I want to find the formula in terms of only the first term and the common ratio. Exactly like here, you see, the first term and the common difference. And of course, NO. Yes. So how should I do that this time? Do you have any idea what to do? So let me write it here in front of your eyes. Sn is T1 plus T2 plus T3. Let me continue this. I will reach to Tn, but of course, what is the previous term? The previous term is Tn minus 3. I want to find a formula for this. So what is the good way to do that? Yes, Dennis?
I don't know if it will help, but you can reverse order and instead of adding, then you can multiply.
No, but that would be very, very hard. Can you imagine? If I reverse the order, and then if I multiply them, you know that how many terms will be involved, you know?
Multiply that.
No, you cannot do that. You cannot multiply term by term. You can take the whole expression and multiply it by the whole expression. So it means that I have to take the first one and multiply it not only to the first one, but all the terms, and do the same thing with the next one. So this method doesn't work here. Yes?
I mean, by seeing that all of them will contain T1, you can factor T1 out.
Yes?
And then in the brackets you will have r to the power of 0, r to the power of 1, etc.
Yes?
And 0, 1 is a arithmetic progression.
Okay, that doesn't help. Because you have the sum of them. Yeah, what you are saying, I understand. You say that I take T1 out, and then it becomes 1 plus r squared plus up to Rn minus 1. But I don't know how. Actually, that is the problem. How should I find the formula for this sum? If it was r times r, 1 times r squared times up to Rn minus 1, you are right. Then I could write r, and then I can add the exponents, and then nicely the exponents become, the sum of the exponent becomes actually an arithmetic progression. This is why this is it. Actually, this is the problem. The problem is that how can I find this? Because this problem that you are referring to right now is more or less equivalent to my problem. So this is a very famous sum. I want you to remember that. So you see that I started with number 1, I multiplied each time by nr, and I added up to r to the power of n minus 1. You want to find the formula for this. Yes. But how should I do that? It's not hard at all. Yes?
The difference between each one is an r. So it's like kind of goes in a loop if you want to use like geometric progression to describe the...
Okay, but I'm listening to you. What should I do in practice?
I don't know.
Oh, no, wait.
Any ideas? Try to do something to get rid of more of the terms. Most of the terms. I want to do something and then I want to subtract 2/10 to be able to get rid of many terms in one go. Okay. Let me follow you. I want to write Sn as everyone I think understood what's going on, yes? So let me write it T1, and the next one is T1 times R, the next one is T1 times R squared, and it will continue. The last one becomes T1 R to the power of n minus 1. Can you tell me what is the previous one?
T1 times R n minus 2.
2, yes? Now, let me multiply this by only R. Yes? So R, Sn, becomes what? Becomes T1 times R. And if you don't mind, let me multiply it by negative R. This becomes negative T1R. The second term becomes negative T1, but R squared. The next one becomes negative T1 R cubed. And this will continue. When I reach here, it becomes negative T1 R to the power of n minus 1. Then I will get negative T1 R to the power of n. Is that right? I just wrote the formula here instead of each term, and then I multiply this by minus R. And then I add these two side by side, yes? If I add these two, the left-hand side becomes Sn minus RSn. But the right-hand side, what will happen? This will survive, yes? There is no terms cancelling this one. So T1 will be left. But every other term will cancel out, yes? Because this one is the positive of this one. And this one will be positive of this one. And this one will be cancelled with the next term. And then what will happen? This one cancel that one. This one is cancelled with the previous one. So another term will survive. So that's your formula. Yes? I factor Sn out. It becomes 1 minus R Sn equals to what? T1, I factor it out 1 minus Rn. And then I want to find Sn. So I got it. So it is T1, 1 minus R to the power of n divided by 1 minus R. On the one condition, what is the condition?
That R isn't 1.
R isn't 1. Yes? If R is 1, the problem is not hard. It's even simpler. Why? Every term is the same.
Yeah.
Yes? If R is 1, all these terms are the same number, and if I want to add the same number n number of times, I just multiply it by n. So the only problem in front of me is in the case where R is not equal to 1. So let me emphasize here, R is not equal to 1. If someone asks you what happens if R is equal to 1, you would say that the problem even becomes simpler. I don't need any formula for that, yes? So the question mark, I want to erase it and write this. I would write Sn is equal to T1, 1 minus the common ratio to the power n divided by 1 minus R. Or some books I have seen write it in the different order. It doesn't matter, because if you multiply the numerator by a negative sign, I have to swap them. It becomes Rn minus 1. And then, of course, I can also multiply the denominator. Yes? So these two formulas are actually completely equivalent, and both of them are true if R is not equal to 1. Usually, if R is smaller than 1, we use this formula. If R is greater than 1, we use this formula. But that is not mandatory. The answers will be the same. So all these formulas that you see will be given to you in the formula sheet. I think in the formula sheet, instead of R, they have written K. So remember that. Okay, and then you realize now, do you know the answer to 1 up to Rn minus 1? What is the answer? Okay, so what's the answer? 1 plus r squared plus r to the power of 3 up to r to the power of n minus 1. Okay, if I want to add them, first of all, can you tell me how many terms you see here? How many summands you see? How many of them are there?
I see 4 or 5.
No, summands means from the first term up to, if you still write all of them, including what is inside the dots. It is n. N terms, yes?
Yeah.
Not n minus 1 terms.
Yes, it's n.
Yes?
Who said it?
I didn't hear that. Yes? But it is n terms. Don't say n minus 1 term, because from 1 up to n minus 1 is n minus 1 numbers, but there is another number. So there are n terms involved here. So what is the first term? The first term is 1. Let me use this one. The first term is 1 multiplied by 1 minus, the common ratio is r, to the power of the number of terms divided by this one. So you get this formula. Or if you want to, you can write it as Rn minus 1, R minus 1. Yes? If R is not equal to 1. And then you get a very nice formula for factorization. Yes? Because why? If I multiply everything by R minus 1, what will happen? So it becomes R minus 1 times this. Yes, is equal to r to the power of n minus 1. So that's a nice formula for factorizing things, yes? This formula for conjugate pattern is clear. Yes, if I choose n equals to 2, what will happen? Let me write it in the other way around. So I would write it r minus 1. Instead of this sum, I write r to the power of n minus 1 plus r to the power of n minus 2 up to r squared plus r plus 1 is equal to r to the power of n minus 1. If I choose n equals to 2, then it becomes what? R minus 1. Can you tell me what will happen for this if n is equal to 2? If n is equal to 2, what can I write for the second pair of brackets? What should I write? Come on.
R plus 1.
R plus 1. Why would you hesitate to say? So it becomes R plus 1. Why? Because when I put n equal to 2, it becomes R. I am supposed to start from 1 unit less and continue subtracting the exponents 1 by 1 until I reach to 1. I did it, and then instead of n, I put 2. But this is a famous identity, yes?
Yeah.
It's the conjugate pattern.
Yes.
But the point is that you were able to modify the conjugate pattern for higher powers. Yes? So let me choose n equal to 3. Then what should I write? Still r minus 1 is r minus 1, but can you tell me what will happen for this sum? I start with r to the power of 2, and then go to the next one, r, and then go to the next one, 1. This becomes r cubed minus 1. So that is the factorization for r3 minus 1 coming from this context, yes? So I don't know, you can write this for n equals to 7. Then you have r minus 1. It starts from r to the power of 6, r to the power of 5, r to the power of 4, r to the power of 3, r2, r plus 1 is equal to r7 minus 1. So if I ask you factorize that, so far you didn't know how to do it, but now you know, yes? R to the power of 7 minus 1 can be factorized in this form, to 2 pair of brackets. So that's one application of this formula. Another thing is, a little bit counterintuitive. By the way, I haven't talked about sigma notation. How many of you don't know the sigma notation?
What?
Do you know this sigma? Okay, so what means that I have to this? Have you seen this sigma?
Oh yeah, yeah.
Okay, so it means the sum.
Yes.
Okay. So this is why I haven't used that so far. So when I say sigma of t sub k, and I write k goes from 5 to 10, for example, what does it mean? It means replace k with 5, replace k with the next number 6, and do the same thing until you reach to 10, and then add them up. That is the meaning of sigma notation.
Yes.
So I will use it probably in the exam. I just want you to know, because in the book you see this sigma notation. Okay, let me now ask you one question. If I have this sum, if I have this, not sum, just the sequence of natural numbers.
Yes.
This is not a geometric progression, but this is an arithmetic progression. So, what do you think will happen if I add these numbers and I increase the value of the last term? So I will continue, for example, over and over again. So what will happen for the sum? It will increase, but how much? Infinitely very big, yes? It becomes infinitely very big. So if I add these numbers, so by the way, what is the formula Sn for this sum up to the nth term? It becomes n times n plus 1 divided by 2. This is a very famous formula. And it is clear that if I take the limit of Sn and send n to infinity, make n very large, what happens? It becomes very large. Yes?
Yes.
Let us think about, in arithmetic progressions, this is always the case. Either it becomes positive infinity or negative infinity.
Oh.
Why is that?
Because
what is the general formula for Sn? The general formula for Sn is n times 2t1 plus n minus 1d, and then divided by 2. Yes?
Oh yeah.
When I increase n, this part increases to positive values.
Yeah.
This is a constant, so it will not change. This also becomes infinitely large.
Yeah.
But then, if d is positive, this is a positive infinity, multiplied by another positive infinity, it becomes positive infinity.
Yeah.
And if this is a negative value, this becomes positive infinity times negative infinity. Again, at the end, it becomes negative infinity. So there is nothing interesting to talk about the limit of the Sn for arithmetic progressions when n becomes very large. Now let us see the same scenario for a geometric progression. That is also another part of your lesson. Okay. So instead of arithmetic progression that I have written here, let me write this geometric progression. So this time I start with 2. Every time I multiply by 3. Yes? So it becomes 6. And then I multiply it by 3, it becomes 18. Multiplied by 3, 54. I don't know, 162, etc., etc. Now I want to ask you the same question. Now assume that Sn is the sum of the nth term of this. Intuitively, if I ask you what is the limit of this when n becomes very, very big, still I think intuitively for this is this clear. What's the answer? Intuitively it is clear. Yes, I am adding all these numbers. It's infinite. A positive infinity, yes. It's clear. But now let me change the scenario. This time, instead of multiplying it by 3, let me every time multiply it by 1/2.
1/2.
And then it becomes 1/2. The next one becomes 1/4. The next one is 1/8 and continues. Now I ask you to add all these numbers infinitely many times.
Is it still positive?
Yeah, it is still positive.
Yeah.
Yeah, it is definitely positive. But do you think it will grow very big or not?
No, it will just be.
How do you know that? Of course, each term It's becoming smaller, no doubt for that. But I am adding a small number to it.
Oh, you never know when it stops.
That's the question. Is there any way to know, or it is not known, or we can find a way to do that? Yes?
It's gonna be
It is positive infinity still if you add all of them.
Okay, how many of you agree?
If you add all of them.
Yeah.
Adding all of them.
Yes.
Yes, it should be, it gets close to positive infinity.
Yeah.
So it means that even if I am adding these things, they are getting smaller, but the number of terms is infinitely. So each term I am adding something, yes?
Yes.
Except that it is wrong. Yes?
You made us wait.
So, yeah, it is wrong.
Att två linjer
So let us, by the way, yes.
So what is it then?
What?
I don't know, but it approaches a number. It doesn't become very big.
Of course not. It will become smaller.
No, we can. Okay, but intuitively it seems that it should reach. I want to.
Because there's so many, you never know when it stops.
It will never get.
Yeah. Okay, that's exactly. So I want to see in the competition. There is a competition here. Yes.
Yeah.
The terms are getting smaller, but the number of terms are growing.
Yes.
So so there is a competition between the number of terms and the value of the terms. We have to see which one will win. Yes?
Do you remember the question about you had like 10 stones in a bag or something?
Yes.
If you remove the 10th one
Yes.
each time,
Yes.
then that would become infinity. But
Yeah.
if you remove the first one each time,
Yes.
it would become 0.
Okay. Yeah.
It feels like this should become infinity.
No, this problem is much simpler than that problem. Okay. Let me try to calculate it together. You want to calculate what will happen if I increase the number of terms, but in this pattern. We have a formula for it, not for infinitely many long series, but for the first term up to the nth term. Yes? So if I ask you, can you calculate Sn? Definitely the answer is yes. I raised the formula. The formula was T1, 1 minus Rn divided by 1 minus R. Yes?
Yes.
So let us put the values here. Instead of T1, I put 2. Instead of R, I should put 1 over 2, but to the power of n. In the denominator, I should write 1 minus 1 over 2. Let me simplify this a little bit. 1 minus 1 over 2 is 1 over 2, but this 2 will go here and become 4. So this becomes, so Dennis, you are right. S becomes 4 minus 4. So let me write it like this. 4, 1 minus 1 over 2 to the power of n. So this is not magic. Yes, we got the formula. I'm just using it. But from the first term to the nth term, now I am asking you send n to infinity. What happens?
Oh wait, we're making this smaller.
Yes. So this number is between 0 and 1. When you raise it to higher power, instead of making it bigger, you are making it small. You can view it from a different perspective. You can write it as 1. 4, 1 minus 1 over 2 to the power of n. Because 1 to power n is 1, 2 to power n. Now tell me, if I increase n, what will happen to the denominator? Only to the denominator. It becomes very big. If it becomes very big, 1 divided by a very big number is negligible. And 1 minus negligible is 1, and you multiply it by 4, it becomes 4. So the limit of Sn, n goes to infinity, is equal to 4.
Oh my God.
Yes? So it means that if you add all these numbers, you will approach to 4, not more. If you do it infinitely many times. And because we cannot do it infinitely many times, it means that we get very close to 4 if we increase the number of terms and add them together. But we cannot go beyond that. And by the way, it is always smaller than 4 because this number is smaller than 1. So it cannot pass even 4, let alone infinity, yes? It doesn't reach to 5 at all. But this don't think that this is always taken for granted. There is a very, very famous series, and that is called harmonic series, because that is related to the harmonics, harmonic frequencies. So, but this is a very simple one, and, but this is not geometric progression. So you have this sigma, you have only 1 over n. It's a very, very simple sigma, and n starts from 1 to infinity. Okay, we want to see what happens to this series. So what does it mean? It means that instead of n I put 1, instead of n I put 2, instead of n I put 3, and I add them. It continues forever. This is called harmonic series. But of course, this harmonic series is neither an arithmetic progression nor a geometric progression, yes? Because from this term to this term, nothing is being constantly added, nothing is being constantly multiplied. So that is a series, but neither a geometric one nor an arithmetic one. So here, what is your intuition about that? If I start adding these numbers, what will happen? It's a little bit counterintuitive. So one feeling that you can get is take GeoGebra and calculate it from 1 up to 100, and then go from 1 to 1000, and then go. Okay, and then I calculated, I think, using Wolfram Alpha. I think if you go to 1 up to 100 million, it becomes around 100. Yes. So if you go from 1 up to 100 million, it reaches approximately to 100, around that. Now my question is again for you. Okay, I'm not cheating. I don't remember the exact numbers, but that would be around these numbers. Okay, then what will happen? Do you think if I start continuing this sum, it will reach to infinity or not? I'm telling you, nearly 100 million terms, it reaches approximately to 100. Now my question is that, let me be a little bit stubborn and continue my way until 1 trillion, 10 trillions, and then I add and add. Okay? So what will happen, do you think?
What will happen?
It's really counterintuitive, but the sum becomes infinitely large.
But it's not
Yes.
counterintuitive because
No, it is
if you want to
counterintuitive.
add that, you have to multiply everyone. If your last term is 1 over 100,
So I told
then you have
so
to
you didn't listen
multiply so
to
that all the
all the numerators are 1,
Yeah,
the
exactly.
denominators are getting smaller. Exactly
Yeah.
like this. No, listen to me. That is more or less. So I mean that exact calculation is needed. Intuition is not enough. Because here, forget about this 2. If I ask you what is this sum, what is your answer? Immediately. It approaches 2. Yes, because I start from 2 and add it becomes 4. So if I clean the first 2, the sum becomes 2. So you see, this is exactly more or less the same thing. Of course, there are some terms missing. For example, from 1 to 1 over 2, they are exactly the same.
Yeah.
But then I jumped to 1 over 4, I missed 1 over 3. I am missing something in between. Okay?
Yeah.
And by the way, this is very strange, yes, isn't it? Because I am missing terms in between. I am telling you that the sum of this one is 4, even if apparently I am missing, that is now close to your idea. But now I am saying that if I add them, yes, it becomes infinity. Yes, I don't want to prove it for you, but trying to convince yourself that this sum becomes infinity is not hard, but is a little bit technical. You need to do it in a smart way. Okay, so that you can convince yourself that this sum approaches infinity. Even though after 100 million terms, I just reached close to just 100. And after 100 million, the next one is 1 over 100 million, 1. Then it is very negligible. I am just adding those negligible numbers on top of each other. and then I am claiming that eventually it becomes infinity. Yes? No.
1 plus 1 over 2 plus 1 over 4 is that sequence. And then it's gonna like be equal to about 2. And 1 over 3 plus 1 over 9, etc.
Exactly. That is the idea behind how to show it. Yeah, exactly. So you need to probably write this as powers of 2, 1 over powers of 2, and then group them and add them, and then convince yourself that eventually it will grow very much. So I want to tell you that for these kinds of calculations, don't rely that much on your intuition. And then it is very nice if I write 1 over n to the power of 1 0.000000, I don't know, even if you want to make it 001, then it converges to a number. Yes? So you see, if n is 1, it goes to infinity. If I just slightly increase this power, then suddenly it converges. That is the word that people use. If the sum is infinity, they say the series diverges. If the sum is a finite number like this, we can say that this series converges to 4. Yes? That is the word that you need to learn.
Convergence.
Yes?
So if n equals 1, it reaches infinity. But
No, not n, the power of n.
Okay.
The power of n is 1 here. So it is 1 over 1, 1 over 2 to the power of 1, 1 over 3 to the power of 1, etc.
Yeah, but if
this
it was,
goes to infinity. But if it is a slightly even bigger,
it gets to 1.
no, I don't know to which value, but I am sure that it will converge to a finite number. Which number you ask me, I don't know. In mathematics, we can have estimates for that, but we cannot find the exact one. Yes? Okay, so this is what I want you to learn about this. Then the next part is to solve some fun problems. Yes? Okay, we want to have solved problems. And then this lesson is finished. Next time I will start the last part, and then we have to negotiate for time for the exam. Yes? I think we can do it before the new year. Yes? So the next lesson is actually very important. I want to spend some time on it, but this lesson is not very conceptual. Of course it could be, but not that very much. It's more technical. Okay, let me ask you some questions. So, let me write some questions. I don't know, should I wait for you to solve it or should I solve it myself? Example. I skip very simple ones because that's Math 1C, but let me solve this. In a geometric progression, in a GP, geometric progression, T5 minus T1 is 20. And S4 is 10. Determine R. Okay? So you start solving it until I find better one. another example. So they are really, these first three problems are really simple, and that is exactly what is expected from you to know. But this last one is a little bit more tricky. Yes? I will give you a little bit of time, still we have time. So you can read that one. I have written n digits. Okay, so let us discover a little bit about what we talked about. So, I don't know, the format, this is probably very intelligent, so you really don't need to be careful about the syntaxes you're using. It will probably understand what you mean. So I write sum, and then I will write 1 over n.
Is this free?
Yes? Yeah, for one part of it is free, of course. And by the way, this is the first software that, you see, step-by-step solutions. You ask, for example, calculate the integral. It will calculate you, and but you need to pay for that. Yes? But anyway, so let me write, I don't know, I am a little bit familiar with this language, so I would write 1 from, let me write it up to 100. So you understand what I am doing, yes? I am adding 1 over n when n starts from 1 up to 100, yes? It's 1 plus 1 over 2 plus 1 over 3 up to 1 over 100, yes? Let me ask this Wolfram Alpha to calculate this sum for us.
Oh my God.
Yes? So forget about extra information. This is the exact value. That fraction over that fraction, but this is an approximate value. It's 5.18, yes? And now let me increase this to, I don't know, let me increase it to 1,000 and then calculate it. I don't know, because sometimes you have to pay. Yes. Forget about the exact value. The approximate, this is the exact value written there. You see, this is the fraction line here.
Oh my.
Yes. And then this is the exact value, 7 points. So you see, when I go up to 1,000, it reaches approximately 4.8. Yes. And now let me ask, I don't know how many, because sometimes they limit you about the. Let me just check it. I don't know which number is that, but let's see if we have enough memory. Because it will not, okay, yes.
Oh.
The answer is 42 point something. I don't know which number I put in.
Yeah.
So how many zeros are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 or something. Even it is bigger than 100 million that I said, so I was wrong. I said that up to 100 million reached close to, but this is much more than 100 million and you have reached to 42 point something, yes?
Yeah.
But the point is that, so let me increase the zeros a little bit. Yeah, let me see what happens.
Oh, what?
It is 53. Yes? But, let me increase, I don't know how many zeros I can increase.
Oh my God.
69. Yes, but something is clear. So you should be a little bit suspicious why this does not converge. Can you tell me why? I mean that even if you don't have enough math knowledge, but you have this powerful tool in your hand, you should be able to predict that this sum is not going to converge. Why is that? Do you have a feeling for that? I don't know, let me play some games here, I am interested. Let me see how many zeros we can add. So I don't even know how to read this number. It's 81.
Okay.
Yes? So, but the point is that 10 to the power of 100 is called Google. Yes? 10 to Google Clocks is 10 to the power of 10 to the power of 100. I don't know, but this is of course smaller than that. 10 to the power of 100 means one with 100 zeros in front, yes? But then let me tell you, why do you think, why you should, even though this is growing very, very slowly, you see that? Why should you get this feeling that this series is not going to converge?
Because it's just...
Why is that? Okay, let me ask you, and let me open another one. Wolfram alpha, yes? So let me write this sum now. Sum of this one. 1 over n to the power of, I don't know, 1.1. And then let me write the same n. It goes from 1 to 1000. For example, for the time being. So I am increasing the power slightly. Instead of 1, I have 1.1. Let me calculate this if it is possible. Yes, it is possible. And it is 5 point. It is not big that, it's not that big, even for 1000. But let me see the difference. I increase it to some more zeros. Let us keep it here. And then I calculate it once more. Of course, you should expect that this will increase, and it increased. It increased to 9.32. And let me continue, because I don't have any problems with adding zeros here. Yes? And then let us see what's happening. It becomes 10 over something. Let me increase this. Let me increase this. So you see what is the difference between a convergent series and a divergent series. The convergent series actually, this is the behavior of a convergent series. It is growing at some point, but after a point it doesn't matter how many terms you add. You are gathering around some number. So this is the behavior of a convergent series. Yes? So don't be misunderstood that if it is going very slowly, it is convergent. No. This is, you see that, let me see by the way, I'm very interested to add zeros. How many? Let us fill up this. You see, the first, I don't know, I didn't see the rest one, but I know 1058 is exactly the same. So you see that how many terms I am adding, all of them are gathering around this point. So this is, I would say that the sum of this series is by 2 decimal points. I don't know how many decimal points. If you want to find the correct decimal points, you need to add them term by term to see. But I know that 10 and 58 are stable. So it means that the sum of this series is approximately 10.58. Yes? But this behavior is absent in the previous one. So you see, this was 94. By the way, let us add these ones. Yeah, let us play the game, yes?
That's a lot of it.
Yeah, I don't think it will work, will it? But this is very... Okay.
Oh,
it's 198. So you see it jumped from 92 or something to this one. And even if I add zeros, I'm curious why this is not coming to a halt. So you see, even though you don't see that I'm adding zeros. Yes?
Yeah.
Let us see how it goes. I don't think it will work this time. Do you think?
The next one.
No.
You
Oops.
exceeded.
Now finally we see. Now we succeeded. Yes, it cannot solve. So I mean, this is, I want you to understand the difference between the behavior of a convergent series and a divergent series is not they are increasing slowly or fast. The point is that they are getting accumulated around one particular point. That is the designation, the signature of a convergent series. Yes? So that is also good. I think it's a very good website that you need to know. It's mostly for free, yes? If you don't want to buy how to solve your problems, and it is very, by the way, this is AI. They are trying to answer all sorts of questions. And then I have seen the solution. It is really amazing. It is like a teacher teaching you. It is telling you do this auxiliary variable, then you do this, then do that. It's very simple. Very nice.
Very teacher-like.
Yeah, it is very good. But of course, in some particular problems that are algorithmically possible to solve, it is very hard, for example, give a geometry problem to this and ask him to solve, okay? But that's a project, actually, that, I don't know, I think famous mathematicians are working on some algorithm that you can solve everything and ask everything from a computer. For example, you can give the theorem to a computer, and the computer tells you that the theorem is this correct or not, and gives you the proof. Of course, this is probably very optimistic for this century, but at least they are actually, this Terence Tao and his collaborators are actually working seriously on this project. Okay, so I want to keep those problems for you. I will solve those problems next time. I want you to work on it, and then goodbye.
Yeah.
Yes.